Hi guys, Mr. Rocco. Happy New Year, 2021. I hope you had a nice, relaxing break and everybody is happy and healthy and ready to go here in the new year. So we are going to jump right into a new unit. We finished astronomy before the break, and we're going to move into topic 4, unit 4, which is called Insolation and Energy. This is a fairly short unit. This should take us maybe 2 to 3 weeks tops, and then move on to a larger unit. Unit 5 is weather and climate. That'll be a little bit longer. But let's jump right into Unit 4. This week you're going to have 3 videos. This one should be pretty short, and then this will be just on what is insolation and some terms. The next one is on what happens when insolation enters our atmosphere. And the third video this week will be on the greenhouse effect. And there'll be some worksheets to go with that. As far as lab goes, the Ellipse lab, I pushed the deadline. It was wanted to do Monday, January 4th. I'm going to push it back because I know with the break and everything, and we switched to remote learning there for a little while, so I pushed the lab due date for that one back to Friday, this upcoming Friday, which is January 8th. So make sure you get that Ellipse lab turned in if you haven't done so yet. And again, there's a video on the assignment that shows you how to make those ellipses. Okay, so let's jump right into insolation. So the term insolation is not insulation. Notice right here it's INSOL. Not with a U. If this was a U, insulation, that's the stuff in your walls that keeps your house warm in the winter. This is the Spanish word for sun, right? If you take Spanish in school, sol meaning sun. So anything that has to do with insolation with an O has to do with solar, which is energy coming from the sun. So insolation, breaking it down into 3 parts. The in means incoming, what the earth receives. Solar, sunlight. And then ation is radiation, which is energy. Anything radiation has to do with energy. So insolation is the energy that we receive from the sun. That's all it is. The energy that we receive from the sun. Insolation. The sun, on average, is, if you recall from astronomy, is 93 million miles away. And so at the rate at which light travels, which travels at 186,000 miles per second, if you take that number into that 93 million, it takes a little over 8 minutes for insolation to reach us. So sunlight that's coming from the sun takes a little over 8 minutes to reach us from the sun. We receive a bunch of insolation, not just sunlight. Yes, visible light is important. That's our most intense. The word intense means strength. So the maximum intensity that we need is the visible light, which is the part, plants turn into using photosynthesis, turn it into energy. We use that visible light to then convert it into heat. We'll talk more about that, and that's what heats the air. But basically, and this is in your reference table, if you go to page 14, it's in the middle of page 14, you'll see this spectrum. It's called the electromagnetic spectrum. Energy has 2 properties, electrical properties and magnetic properties. And so they put the term electrical and magnetic together to make a big word called electromagnetic. And so all energy is broken down by what's called the wavelength. Light and energy is traveling like this. We'll talk more about that later on as well in this unit. They're called transverse waves. They kind of look like ocean waves going up and down, up and down. And the length of each wave is what determines the power, I guess, or the power of the wave. Shorter wavelengths are going to be over here on the left. And the rule of thumb is the shorter the wavelength, the more powerful the energy is. So wavelengths over on this side, on the left-hand side of the spectrum, are short wave. I couldn't even draw them. They'd be like up and down, up and down, up and down, really bunched together, like microscopic wavelengths. And those are going to be things that are coming from the sun. Gamma rays, X-rays, ultraviolet, and of course visible light. So everything from visible light would be right in here. Anything from here over to the left is coming from the sun. So these are all part of the insolation, the gamma rays, the X-rays, the ultraviolet, and the visible light. Then you take this visible light and it's broken up into the colors, right? Roy G. Biv, when you look at a rainbow. And so you've got your red, orange, yellow, green, blue, and violet. Again, broken down by wavelength. Violet and blue are shorter wavelength. Reds are longer wavelength. And that goes back to, if you remember astronomy, when we did red shift, blue shift. Blue meant a star was approaching Earth, which means the wavelengths are getting squished. So over here, they're going to be, again, much shorter. When you get over to the red side, the waves are going to stretch out much longer. And then after this visible light, you see you've got other things over here, increasing wave. These are even longer. Infrared, which is just heat. Microwaves, right, which we use to cook some of our food and heat things up. And then radio waves. Radio waves are your AM, your FM, your television waves, Sirius XM, satellite radio, all that kind of stuff coming from the satellites in space. These wavelengths are very, very long. I mean, a wave could be, 100 meters long. Again, the longer the wave, the less harmful it is to humans. And so radio waves are going through your house, they're going through your body, they're not hurting you, right? Gamma rays, that's a different story. Gamma rays would kill you in a matter of minutes if you were subjected to high doses of gamma rays. But luckily, the Earth obviously has an atmosphere. That's what protects us from things like gamma rays and X-rays. Unfortunately, we talked about this a while back, right? Ozone, which is up there in the stratosphere. Ozone's main job is to soak up the ultraviolet rays, and that's to protect us from those rays. But unfortunately, the ozone layer, due to pollution, has deteriorated a little bit, especially certain parts of the world, and so more ultraviolet is getting through and not being blocked by the ozone, and that's why you have to be very careful wearing your sunscreen when you're out there in prolonged amount of sun to protect your body from those ultraviolet rays. So anyway, let me clear the screen. Our Earth is going to vary, depends on the day, if it's a bright sunny day or versus a cloudy day. Depending on the day will depend on how much insolation we receive. On a bright, sunny blue sky day, not a cloud in the sky, the ground down here on the surface receives about 75% of that sunlight. We never get 100%, and that's because we don't get this stuff. These things, again, get blocked in the upper part of the atmosphere. The gamma rays, the X-rays, the ultraviolet. We want the visible light, right? That's what we need. But these things, gamma, X-ray, ultraviolets, get blocked out. So even on a bright, sunny day, the atmosphere will allow 75% of insolation to the surface. I'm recording this on Sunday, and we got a little snowstorm coming. And so it's cloudy out today on Sunday, and so the clouds are going to obviously lower the amount of sunlight, and now you're only, on a day like today, because it's overcast, you might only get 50%. So clouds are going to block about 25%. And so bright sunny day, 75%. Cloudy day like today, the surface only gets about 50%. So that's going to be the fluctuation there. It's going to go anywhere from 50% to 75%, depends on if it's cloudy or clear sky. And this chart just shows that. So where the energy goes. So down here, this would be the surface right here. If it's a cloudy day, only about 50% of the sunlight will reach us. Right, 100% is coming into the atmosphere. Right, it's coming from space. There's nothing in space to block the sunlight, so it's coming from the sun, reaching our atmosphere. But by the time it gets to the ground, all of these things happen on the left-hand side. If it's a cloudy day, clouds are going to reflect. They're going to, the ground is going to also do some reflection, especially if you have snow and ice on the ground. You have different gases in the atmosphere that are going to cause reflection. So about, on a cloudy day, you're looking at, 25, 30%, 32% of sunlight gets reflected, which means it gets bounced back up into space. On this side, this is absorption, which means to take in. So again, clouds, dust particles, things up in the atmosphere, you're looking at 18% gets absorbed, which means it never makes it through the atmosphere. So if you take this 32%, right, and you add it to that 18%, 32 plus 18 gives you 50%. And that's why on a cloudy day, you're only getting about 50% of the sunlight that actually makes it to Earth. Never gets to the ground. It all gets filtered out by our atmosphere. Again, if you have a clear blue sky day, you're going to take some of these things away, right? The clouds are not going to be there, so that 21% plus this other 3%, you're going to add that to the ground absorption, and that's why I said earlier 75% on a blue sky day would reach the ground. Again, never 100%. We don't want the gamma rays, the X-rays. That stuff needs to stay up in the atmosphere and away from us. So insolation means sunlight, and then you have what's called angle of insolation, which is the angle of the sun, right? Right now, our angle of the sun is going to be low for us, and that's because we're in our winter season. If you were to go right now to Rio de Janeiro, Brazil, or Australia, right, go to the southern hemisphere, well, they have a higher angle of insolation because the sun is at a much higher angle for them, being that they're leaning toward the sun, whereas the north axis is leaning away from the sun, right? We went over seasons when we did astronomy. So location has a lot to do with your angle. All right, we have a low angle of insolation. We have passed the first day of winter officially. If you recall, that was on December 21. And so since December 21 now, we're a couple weeks past that date, our sun angle is going to start to increase, right? Our days are going to slowly start to get longer, and you'll start to notice that over the next couple weeks. You'll say, oh, I can tell it's not getting dark at 4:30 now. It gets dark at 5 o'clock, and then eventually 5:30, 6 o'clock, etc., right? As our days get longer, our angle of our sun goes up, right? The sun's starting to creep back the other way and come back toward the northern hemisphere as we head back towards summer. This is going to show you two different types of rays. So being that we're in a winter and we have a low sun, what we get right now are what they call the oblique rays. And oblique rays, if you think of on your body, you have oblique muscles. These are the muscles along the side edge of your stomach. So not where your belly button is, but on the sides. You know, people that want to have, what do you call it, a six-pack, right? They have these ripples in their stomach muscles, right, when they work out and exercise their core, right? So those are your obliques. They're on the side. So if you remember, oblique muscles are on the side. Oblique rays are the same thing. They come in on the side. And if you look here, this is the sun ray coming in. It's a larger area of sunlight, and what you're doing is you're spreading that sunlight out over a larger area, but therefore when you do that, you're making it less concentrated. And so that's what keeps your temperatures down. The sun is at a low angle, and it's spreading that sunlight out because it's coming in low, and therefore you're not getting that intense sun. And that's what we have right now. That's what causes winter. We have the oblique rays because the sun right now is maybe, 25 degrees. That's probably our highest angle right now at noontime, which is a very low angle. If you go down to Rio de Janeiro or Australia right now, Australia's temperatures are near 100, right? 95, 100 degrees right now in Australia because they're getting the opposite. They're getting the vertical rays. And that we talked about that in astronomy. Vertical rays, let's say this is the surface, right? Oblique rays are coming in over here from the side, low angle, which is spreading out the sunlight. A vertical ray is coming straight down overhead. That's your 90-degree angle. And so that's what's going to create a smaller area. See, and it says here, smaller area receives a greater concentration of insolation. Again, sunlight is insolation. So notice the circle here. Up here, it was spread out. Here, it's a much more concentrated, smaller circle, which means you're going to create a much more intense temperature, right? That's your summer. And so depending on the season will depend on what rays we get. So right now in December and January, we are always getting these oblique rays where it spreads the sunlight out over a larger area, creates less sunlight, less concentration, right? Keeps us colder. When we get to June, 6 months from now, we won't be getting oblique rays anymore. We'll switch to vertical rays, and we'll be getting a smaller area of concentration, a smaller area, I should say, which gets a greater concentration, right? It's more intense sunlight, right? When those vertical rays are coming straight down on top of us. This is a YouTube clip on sunlight. They're called crepuscular rays. I'm going to pull this up. It's a YouTube clip. Let me do that right now.
You know those pictures that your parents and your friends and your parents' friends are always posting all over social media? The ones that have some sort of inspirational quote plus a picture where the sun seems like it's using beams of light to break through a wall of clouds? Those trails of light are called crepuscular rays, and they are actually pretty common. If you look at the sky on a partly cloudy day, especially if it's around dawn or dusk, odds are you will see those rays for yourself, though you probably won't see any inspirational quotes floating around in the air. Crepuscular rays happen when sunlight passes through air that has a bunch of stuff in it. Sunlight is always bouncing off of stuff in the air. The way it bounces depends on what it's hitting. Nitrogen in the air, for example, scatters the bluer parts of the sun's light, which is why the sky is blue. Crepuscular rays happen when the sunlight hits bigger particles, like dust and water, which bounce all the light's colors pretty equally. And when we see all the colors of light at once, we call that white light, which is why a lot of crepuscular rays look white. Sometimes the rays don't look white, which just means that the light hitting them wasn't white to begin with. So crepuscular rays around sunset will be redder, since sunlight looks pretty red by that point. But crepuscular rays aren't always visible whenever there's a lot of dust or moisture in the air. There also needs to be something blocking some of the sunlight. Without anything in the way, we wouldn't be able to see the paths of the individual rays no matter how much stuff was in the air. Light would be bouncing off of everywhere equally, and everything would look equally lit up. These two things, particles in the air and something to block parts of the sunlight, are why clouds are so common in those Facebook pictures. Clouds are denser pockets of water vapor and dust that are really good at blocking sunlight, and the area around clouds also tends to have some dust and water, so if some light does manage to break through a hole in the clouds, it hits a whole bunch of material that scatters it. But you don't need clouds. Mountains and buildings can also create crepuscular rays, and if the sun is at the horizon, like at dawn or dusk, you can get crepuscular rays that stretch all the way across the sky. So intense. Like all crepuscular rays, they look like they're radiating out from the sun, like a bunch of lines coming from a single point. But the ones right above you will look parallel, and the rays going behind you, directly opposite where the sun is, all meet again where they are called anti-crepuscular rays. And they look like they're radiating out from some invisible sun on the darker side of the horizon. So what's actually happening here? Are the rays parallel, or do they spread out from the sun? Well, both. The sun is so far away that when its light gets to Earth, it's all pretty much going in the same direction. So all of the sunlight causing crepuscular rays is virtually parallel, which means that the rays themselves are always parallel lines. They just look like they're meeting at the sun because of perspective, which makes things look smaller when they're farther away. Just like how train tracks look parallel when you're standing next to them, but they look like they're getting closer together the farther away they are from you. So those beginnings of crepuscular rays far away from you are like those distant train tracks that seem like there's hardly any space between them. Then the rays directly above you are like the train tracks by your feet, so they look parallel. But the anti-crepuscular rays are also really far away from you. They're just as far away as the original ones. So they look like they're coming together just like the original crepuscular rays did. If you could see crepuscular rays from space, you would see them for the parallel lines that they really are. And this is a thing that we know, because astronauts have seen crepuscular rays from space, and this is what they see. So the next time someone puts up some photos of supposedly inspirational crepuscular rays, don't forget to congratulate them on their excellent picture of dusty light. Thanks for watching this episode of SciShow, which was brought to you, of course, by our patrons on Patreon. Thank you, people. Thank you so much.
Okay. So those are kind of cool, those crepuscular rays. All right, so again, when it comes to insolation and the angle of insolation, the curvature of the Earth is really what affects that angle of the sunlight, the angle of insolation, right? Rhinebeck, I put a little dot. So right now, right, we're receiving a low angle, right? Which again, you can see in this, sort of in this diagram here, those are those oblique rays. Notice the sunlight, if it's coming in low, notice how the sunlight, I'll kind of highlight it, is stretched out here. You have a large area being hit by sunlight, but that spreads the sunlight out, which again lowers the intensity, the strength of it, the concentration. As you get toward the equator, which is, we know, the hottest part of the Earth, notice the sunlight rays are coming in directly overhead. So these are the oblique rays, I'll put O. These are the vertical rays, V. And notice when they come in and hit the equator, notice this concentration of sunlight is much smaller. See, up here it was spread out. Here it's much more concentrated, right? Concentrated sunlight, hotter temperatures. Then you get back down here to the South Pole, same thing as up here closer to the North Pole, the rays get spread out again. So these are those oblique rays again. Notice how they spread out, and again, That's going to cause less concentration, which spreads it out and becomes colder. So you've got oblique rays as you get closer to the poles, low sun and oblique, and as you get closer to the equator is where you're going to find your vertical rays. This is showing you, again, we've looked at this before, the paths of the seasons. And so the winter solstice, which was a few weeks ago, this is this path over here, the short path. This is showing you 40 degrees north. Rhinebeck is about 42 north, so this would be New York City-ish, close to New York City. But, you know, roughly what we would have as well. So if you remember, go back a couple weeks ago, and even right now, we're not that far past the first day of winter, our sunrise to sunset time. So the sun really gets going at about 7:30 in the mornings when it rises, and it sets at around 4:30. And we bottomed out at like 9 hours of daylight. So those were our shortest days. When we get to March, right, 3 months from now, and again, you're going to notice it gradually. The sun's going to move higher. The angle of the sun, or angle of insolation, as it goes up over the next 3 months, the days are going to get longer. Our sunrise will go from 7:30 in the morning, and get even earlier. We'll get back to around 6 o'clock in the morning. And the sun won't set till 6 o'clock at night. And then we'll reach the spring equinox, right? Notice 12 hours, 6 to 6 is our 12 hours of daylight. And then by the time we get to the end of this school year, in June, when we reach the summer solstice, now we're talking early sunrise. It wouldn't be 4:30 because, remember, in the spring we turn the clock, so we have to spring ahead. So add an hour here. So this would be 5:30 would be a sunrise, and that's accurate. And sunset would be, instead of 7:30, push this back an hour, make it 8:30. And that's what's going to happen when we get to summer, and we have 15 hours of daylight, right? A much longer daylight period. So we'll go from a 5:30 in the morning sunrise to an 8:30 at night sunset. And so that's our seasons. So again, Santa Claus, for those of you that celebrate Christmas, right? This time of year, he's got very little sun up there. It's dark, right? 24 hours of darkness. And his angle of insolation is very, very low, which explains why it's cold at the North Pole. For us, we're considered what they call middle latitude, the United States, New York State. We're in the middle latitude region, right in here. And so we go from fluctuation, right? Hot in the summer, 6 months later, cold in the winter, and then back again. And then people that live at the equator, they tend to have the highest angle of insolation, and therefore, because it's the highest angle, they're getting those, again, V, I'll put for vertical, those straight rays directly overhead, and that's what creates that intense, concentrated sunlight at the equator, which keeps it hot. The word intensity means strength. So when you see intensity of insolation, right? So we've covered a few words here. Insolation just means sunlight, or energy that we're receiving from the sun. Angle of insolation is the angle at which that sunlight's hitting that surface. And then intensity is what is the strength of the sun's energy. And again, if you think about using, let's say you used a flashlight, right? If you shine a flashlight straight down from above, that's creating those vertical rays. I'll put V. That's going to create that concentrated light on the floor, right? If you took a flashlight at home, you can try this. Just shoot it straight down onto the floor. You get a very small circle of flashlight right on the floor, right? Very intense, right? Higher angle, more intense. If you took that flashlight and kind of put it off down to the side and made like a low angle, right, off to the side, those are those obliques. I'll put O for oblique. Make an oblique angle. Notice what happens to the sunlight when it hits the floor. It spreads out again. It scatters and creates a less intense sunlight. So the higher the sun, the more intense. And vice versa. The lower the sun angle, the less intense. Our sun angle is going to change through even on a daily basis, right? In the morning, the sun is down low in the sky as it's just coming up over the horizon. So that's a low angle, right? And the sun isn't as intense. So that's why it tends to be cooler in the morning. Then the sun's going to move, right? It's going to appear to rise, going to go across the sky, and you're going to reach what's called solar noon, which is when it reaches its peak. Well, that's when it's going to give you its most intense sunlight. So even in the winter, the sun, like, yesterday was Saturday. We had a pretty decent day. It was getting close to 50 degrees. Well, we didn't reach that peak temperature till later in the day, but as the sun went up, so did the temperatures, right? A direct relationship. The angle of the sun came up, so did the temperatures, and we eventually reached close to 50 degrees. Then, as the sun went down yesterday in the afternoon and the evening, as it went towards sunset, so did the temperatures, right? And they dropped off eventually as the sun went down. So angle and temperature really are direct hand in hand, right? Angle of the sun goes up, so does the intensity, so does the temperature. Angle goes down, so does the intensity, so does the temperature. So they're all interconnected. They're all related to each other. And then the word vertical ray, we covered this in astronomy, but just to go back at it one more time, was when the sun is at 90 degrees. All right, so if this is the ground, the sun is coming directly down on top of the surface, creating that right angle right here. Again, we never see the sun at a vertical ray. Our sun, even in June, when we reach our peak angle for us in Rhinebeck, we reach about a 71, 72 degree angle. That's the highest our sun will get to. Remember that the sun stays between the tropics. So June 21st, even though that's our longest day, the sun doesn't get above 90 unless you're at the Tropic of Cancer, which is 23.5 degrees north. That's way down toward Cuba and the Caribbean. So you'd have to go down to Cuba and the Caribbean to see the sun at the vertical ray. This time of year, again, December, the sun, remember, is more in the southern hemisphere, and that's in that Tropic of Capricorn, which is in Australia and Madagascar and South America. And then in March and September, remember, these are equinoxes. That's the way I remember it. On an equinox, first day of spring or first day of fall, the sun is directly over the equator. All right. So again, because we never see the sun at 90, let's say this is the Earth here, right? And this is Tropic of Cancer. We'll call this the equator, and then we'll call this Capricorn. New York, I'll put an X. We're up here. In order to see the sun stays in this region, the vertical rays. We always have to look south to see the sun, right? Solar panels face south. Put a lot of windows on the south-facing side of your house to receive all that wonderful sunlight. Especially this time of year, you can really soak up a lot of sunlight, open the curtains, and have a lot of south-facing windows, and that's going to really let in all that free energy, so to speak, from the sun. And I think that is going to be it for, yes, this first video. So I will post this. Actually, I'm going to put these on. I created a YouTube channel, and I'm going to put this on my YouTube channel. I'll put a link to my YouTube channel. Do me a favor, please subscribe. Not looking to make a lot of money off YouTube, but I think the issue came up with Canvas. In order to the beginning of the year, I was saving my videos onto Canvas, but Canvas only allows so much gigabytes of storage, and I ran out of storage because I make a lot of videos, and videos take up a lot of space, as you probably know. And so over the break, I created my own YouTube channel. So I'm going to put this video, it's going to be on YouTube. The link will be on Canvas. You just have to click on the link. It's going to take you to YouTube. So if you notice YouTube pop up, that's what it's supposed to do. But when you're on that YouTube channel, please feel free to subscribe. I'd like to see how many people I get. And that's it for this video, and I will talk to you soon. Bye.